Welcome to the course organized by the International Center of Applied and Pure Mathematics. The course or the lecture is titled Semi-Free Resolution and Application. The aims of this course is focus on the proof of the Jones theorem where this denotes the Hochschild cohomology of the normalized singular quotient x, and this denotes the free loops cohomology space. Indeed, what we want to prove here is to what we want to do here is to give a new proof of this theorem by using the semi-free resolution material. So it is well known that the Hochschild cohomology, that for a given x, a topological space if x, this denote the normalized singular quotient and Lx the free loop space then the Hochschild homology of Nx is isomorphic to the Eilenberg motor of it is also known that the free loops is isomorphic to Nx as NE module, and this is the Eilenberg motor of Nx as n of x times x. So what we are going to prove is to show that these two vector spaces are isomorphic as graduate vector space. Okay. So to do this, we have to recall all the material of homological algebra. This will be the first part of these lectures. So we are going to consider here some convention. K is a field of characteristic P greater than 0 if V is a K vector space, graded vector space, then we have Vi equal to Vi negative I. And if we denote by S the suspension of degree, then SVI is equal to Vi negative 1 and SVI is equal to Vi plus 1. These are the conventions that will be used during these lectures. Okay. So now we will start with homological algebra. Part 1, homological algebra. First step, graduate vector space or module. So we'll define what we call graduate module. M is a graduate module if M is equal to which Mi A K module. And now, if we add to that M a map G from M to M of degree, let's say -1, such that G for all I belonging to Z, Gi is defined from I to Mi -1. Then the couple is a differential graduate module with the condition equal 0. Before going on, let us define first the morphism of two modules, graduate module. M here is a module, M prime is also a graduate module. So we call that this map is a morphism of graduate module of degree k if F is just a family of maps from Mi to Mi plus 1, have here F k belonging here to N and I belonging to Z, where Fi is a k linear map. So the G that we have defined here is an example of this map. Okay. And assume that M D is a differential graduate map, a differential graduate module. Differential graduate module. We have two cases. The first case is when the differential is of degree 1, and the second case, the differential is of degree -1. When the degree of D is +1, that means for all I belonging to Z, we have M we say that the couple MD is a differential graduate module if D if we have this condition, this composite here, here you have d plus 1, di plus di. We have the composite, which is di plus 1 composite by di equals 0. The second case is when the differential, when the map D is of degree -1. We have this situation. We have D I plus composite by d I plus 1 equal 0 for all I belonging to Z. So in the two cases, we have M di I belonging to Z and M I d M I belonging to Z. We have these two type of differential guarded module, which are respectively called, this is a chain complex and this other one is a quotient complex. Now, if you have two chain complex, if you have two chain complex, if we have two chain complex, let's say M G M and M prime D M prime, two chain complex, two chain complex, a map from M dm to M prime d M prime f is just a map which commute with the differential here. That means that for all I belonging to Z, we have the following commutative diagram. Here is the differential. Here we have Fi from M to M prime I. Here we have the differential M prime I, M -1 prime. And here we have F I -1. We have this commutative diagram. Okay. That means that for all I belonging to Z, we have Fi composite by have d I prime composite by F equal to F. Here we have Fi -1 composite by d I. Have this. Okay. Let us remark that the complex we are using here are indexed by on Z. But we can have the complex index in N. That means that we can have a complex M I D I belonging to N. This such complex will be called a positive graduate complex. Of course, we can also have a negative graduate complex. But what we will use in this course is a positive graduate complex. In a similar way, we'll have a quotient complex, a morphism F like this, such that the following diagram commute. So, in the case of the quotient complex, we consider here a quotient and another quotient complex Fi from M to M prime is said to be a map of chain complex if you have this commutative diagram. Means that Fi plus 1 composite by Di equal to D prime I composite by Fi. And the consequence of these two identity means that F can move from the chain complex to the something that will be defined later. Okay. Now that we know what is the chain complex, the quotient complex, we know that what is a map from a chain between two chain complex and two quotient complex, we can say that the family of chain complex with their maps form a category called the category of chain complex. In the similar way, the category of quotient complex will be the family of quotient and J maps, which will be denoted like this. Before, at the beginning, we started with the module and the map. So the category of module and J map will be also denoted by graduate module. The category of differential graduate map will be denoted differential graduate module. So we have built here 4 categories. The first one is the category of chain complex. The second one is the category of quotient complex. The third one is the category of so the first one is the category of chain complex. The second one is the category of quotient complex, and the third one is the category of graduate module. The last one is the category of differential graduate module. Okay. Now that we have already built all these categories, it is better for us to know that if you have A, D, B, D, 2 chain complex, then one can a new chain complex denoted by with the associated differential like this, such that for all x belonging to n, h and the associated differential is given by G equal to D from H to which assigned to GF with G of F equal to okay, here we have A with D of F equal to D B composite by F plus so for A and B, two differential graded module, one can associate a new differential graded module defined like this. For any S, we have this identity, and the associated differential is given by this. Perdu le truc. So what I'm saying here is that for a given differential graded module A and B, one can associate a new differential graded module like this with the associated differential defined like this, so that we have D of F equal to this identity here. Okay. Now, if K is equal to B with the differential dB equal to 0, the above complex become A K such that equal to with the differential deduced from this formula, means that the differential will be this: D of F is equal to negative 1 power F D of A. This is just the consequence of what we did before. when B become the field. Okay. Now that we have defined the cochain complex, the chain complex, and the associated, when you have two chain complex, we can define a new chain complex by using the bifunctor Ohm. We can move to the definition of the B complex. A B complex is what? A B complex is just something like this. Where C here is a module which is bigraduated, means that we have here C is Cp cure P belonging to Z and cure belonging to Z. This is C. And D here is indeed the summation of two differential here. This is the horizontal differential, and this is the horizontal differential, and the second one is the vertical differential. Means that our differential C, our B complex here, C, is just something like this. C0, 1, C0, 2, C0, 3, C0, K. Now let's see S. We have here C1, we start here with C00, C0, C01, C0, C1, 0, C1, 1, C0, C1, 2, C1, 3, C1, S. Okay. We have here D here, D. Here, which D we have here? D, and so on. Okay. So we have here we have D here, D here, D here. Okay. So this differential here is the one that I called here horizontal differential. These are the horizontal differential. Here is the vertical differential. Okay. Okay. Now these two differentials satisfy some conditions. We have this D, V, composite by dV equal 0, equal dH, composite by dH equal 0, equal to dH, composite by dV plus dV, composite by DH. So it has this, all this composition of maps are equal to 0. The importance of this is focused on the if we have a double complex, we can compute a new complex called a total complex is obtained in this way. So from a big complex like this, we have a new complex obtained in this way. The total complex is a new complex. In degree n, we have the total complex in degree n equal to this summation P plus Q equal to n of C, P, Q. Okay. Now that we have all information about complex, it is good for us to move to some important notion which will be called the homology and the cohomology. Okay, consider a chain complex like this, which is indeed I from 1 from 0 to infinity, Ci, and D. This is my chain complex. Okay. Now, I will define a submodule of this chain complex by saying that X belonging to Ci is a cycle if di of x is equal to 0. Okay. The set of all such element is denoted Ci, Zi of C equal to the kernel of Di. Of course, this element, this identity means that we are on the other hand, we have this, an element y belonging to Ci is a boundary if there exists x in Ci plus 1 such that Di plus 1 applied to x equal to y. That means that our y belonging to the range of Di plus 1. The set of all such elements will be denoted Di of C equal to the range of Di plus 1. So, we call homology group of the chain complex C D, and we denote it by CD. This is just a graduate module equal to this is the quotient of two modules, means that okay, this is the quotient of two modules, means that Zi of C contain Bi of C, and this is the identity D composite by D equal to 0. In a similar way, one can define the notion of cohomology. So we consider here a quotient complex we have here is quotient complex. So we call the cocycle of degree I an element x belonging to Ci so that di of that x equal to 0, means that x belong to the kernel of di. And the set of all such elements is denoted Zi of C the coboundary of degree I is an element y belonging to Ci, yes, Ci is here, so that d is here. Di of so that there exists x in C -1 satisfying d I -1 applied to that x is equal to y. Okay. And such element form a set equal to okay. So we have this. So the cohomology of that chain complex is denoted which is a graduate module with equal to Zi of C and this is because G composite by D equals 0, means that the Bi is the submodule of Bi of C is the submodule of Zi of C. Let us remark that the notion of homology that we have defined is a functor from the category of differential graduate module to the graduate module. Means that if we consider here the category of chain complex, category of graduate module, we have here C, D and C prime, D prime, which are two complexes. F here is a morphism of complexes. With this functor we move to the graduate module category by CD, C prime, T prime, such that H of F defined from CD to C prime G prime to each class here we have H of F applied to that class equal to the class of F of X. Okay. We we can use the similar functor. We can do the same thing for the functor cohomology. That means we consider here two quotient complex, and then we move to the graduate module category, and we obtain the morphism of two graduate module. This, what I'm talking about now, is just the recollection of an homological algebra, which is supposed to be known by all students in master degree. Okay, so those who are in PhD degree are supposed to know all these things. Okay, now that we have already defined the notion of homology and homology, we'll move to the notion of homotopy. Homotopy. There are two types of homotopy. The first one is the chain homotopy, and the second one is the cochain homotopy. The chain homotopy is what? You consider C, D, and C prime, D prime, two chain complex. We have here F and G, two morphism of chain complex. We say that the two maps are homotopic if there exists a linear map of degree +1 from C to C prime satisfying some properties. That means for all I belonging to N, we have Hi from Ci to C prime I +1 with the following property. Have here C I -1, Ci +1, sorry, Ci -1, we have here Di I +1, C prime I +1, C prime I, C prime I -1. We have here our two morphisms F and G. Okay. The morphism that I have announced here is this one. Hi -1. We have here the differential D prime I +1 and D prime I. The condition here is that Fi minus Gi is equal to G prime I +1 composed by Hi plus Hi -1, Hi -1 composed by Di. This is the condition for all I belonging to N. So we say that F and G are homotopic if one can find a K-linear map of degree 1 so that we have this identity. One of the consequences of this relation is that if F and G are homotopic, we write it like this. Then in homology we have that the maps obtained in homology are equal. This is one of the consequences of this. Indeed, what we have is Fi Gi equal to d prime I plus 1 composite by fi composite by hi plus hi negative 1 composite by di. If you apply here, if you consider here x belonging to the kernel of di, you apply it to this identity. We have fi applied to x, gi applied to x equal to gi plus 1 prime hi applied to x plus hi negative 1 applied to x. So this one is 0 because x belongs to the kernel of gi. So finally we obtain fi applied to x, gi applied to x equal to g prime e I plus 1 hi applied to x. And this means that these two elements have the same class in homology. Class of fi of x is equal to class of gi of x. And this is equivalent to say that fi applied to class of x equal to gi applied to the class of x. Okay. So the consequence of the fact that the two maps f and g are homotopic means that in homology we have the same are equal. The two maps are equal. Now we have studied here the case of chain homotopy. We can also see the case of cochain homotopy. Maybe it will be better that if someone has a question, they can ask it so that we should ask the question and then continue. Is there any question? Is there any question? I would like to answer some question if there is any question, so that I should continue with the course. If there is no question, let us go on. Okay, the cochain homotopy, we consider now two cochain and two maps of cochain here. We say that the two maps are homotopic, and we write f homotopic to G if there exists a k-linear map H. Let's denote it by H bar from C star to C prime star of degree -1, satisfying some properties. The properties is exactly similar to the one that I gave here. Okay. So when you have two morphisms which are homotopic, either in the cochain case or the chain case, the two are identified in homology or in cohomology. Now let us move to the notion of differential graduate algebra and graduate algebra. we consider here a couple AD, where A is a K graduate module and D is the in on A. So we say that this couple is a differential graduate algebra if firstly we have a graduate module as we defined it before, and then we have a multiplication here which is indeed satisfying the associative axiom, means that I have here M composite by we have M A tensor M, so A tensor A this diagram is commutative, means that we have M A composite by M A tensor equal to M A one A here is the identity map from A to A. The second property, we say that our algebra is commutative if we have M composite by where TA, let's denote it by this, is the map, the interchange map defined from A tensor A to A tensor A okay. And if there exists an element, let us denote it by this in A, such that M of x also equal to x equal to M then 1A called the unit of A. At the beginning, we consider the differential graduate module. So, there this is qu'il faut faire là maintenant. Je ne comprends pas ce qu'il faut faire là. Alors, il y a quelque chose qui est... Quelque chose que je ne comprends pas là, ça, ce n'est pas parti. Ça fait ça. OK. Je suis obstrué là. Je suis obstrué là. We have considered at the beginning this quotient algebra, and we say that this is a differential coordinate algebra if the differential here is a derivation. Means that what? Means that it means that we have M A composed by the identity tensor the differential plus the differential tensor the identity is equal to more precisely we have for all x, y in A, g A of x, y is equal to gx dot y plus negative s g x x dot g a y. That is dA of x dot y equal to dx dot y plus negative degree of x y of d. Okay. Now we have defined what is a differential coordinate algebra. We have to look to study the map between two differential coordinate algebra. A, B, A, D, and A, B. Two differential coordinate algebra. A map from A to B is a map of differential coordinate algebra if F is a map of. Okay. What I'm trying to say here is that I'm trying to define the notion of map between two differential coordinate algebra. So, if A and B are two differential coordinate algebra, a map here is a morphism of differential coordinate algebra means that F is a map of differential coordinate module with the condition A That is F composite by A equal to M, here is M, is MB, MB composite by F tensor F or F all x y in A, F of x dot equal to F of x dot F of y, where here the multiplication here is the multiplication defined here, and the multiplication here is the multiplication defined here. Okay. Now the category of differential graded algebra is just the category whose objects are differential graded algebra are morphism of graded algebra. Okay, so we are going to define the product of the tensor product of graded algebra, the opposite algebra, and the notion of enveloping algebra. We have let A G be a graded algebra. Okay. A here denote here the opposite algebra as vector space equal to A, and the multiplication here we denote it by this R up, tensor R up to A up, such that M A up equal to M A dot A, where G here is map, the interchange map X Y negative X Y Y dot X. That is for all X Y in A up, M up of X Y, X tensor Y is equal to negative degree of X degree of Y, M A X tensor Y. Okay, we have this. So if A AI, if A D A, B D B are two differential graded algebra, one can form a new differential graded algebra like this. Okay. The multiplication here is given by So the formula is alors ça c'est bon. Okay. So the formula is this one. If MA denote the multiplication here, MB denote the multiplication here, then we have MA tensor B is exactly equal to this. This formula is applied to X, applied to this, give us this identity. Now that we know how to define the tensor product of two differential graded algebra, the differential here is given by dA plus, here is B, here is A, tensor dA, here is dB, here is dA, and here we have A here and B here. Okay, this is how the differential is defined. Okay, now that we know how to define the differential graded algebra from two differential graded algebra, we are going to define the enveloping algebra denoted by this, which is the tensor product of the algebra by the opposite algebra, associated opposite algebra. This is how the enveloping algebra is defined. Besides this notion of differential graded algebra, there is a dual notion of this notion called the differential graded coalgebra. So we call differential graded coalgebra a couple like this, where C is and D, the couple C and D is a differential graded module, and the graded module MC, is endowed with the co-multiplication defined from C to C tensor C, which is equivalent in degree C n to C I tensor C G C n here. Here we have indeed this, we have this I plus G equal n C I tensor C G. Okay, have this, satisfying the property of co-associativity, and if the coalgebra is co-commutative, you have some properties that should be satisfied. If you have the unit, you have some property that should be satisfied. for the coassociativity, we have this. So we have this property. If this property is satisfied, that the co-multiplication here is co-associative. So then we have what? We have this. If we denote the interchange map on C like this, and we have, okay, we have C tensor C, T, C tensor C here. We have here the co-multiplication. We have here the co-multiplication. Then TC, C composite by delta C equal to delta C. Then we say that the coalgebra is co-commutative. Alors, je vais suivre. And if there exists a map from C0 to K, C0 here, because our differential graded coalgebra is a graded module, at 0 degree we have this. If there exists a map from this to that, so that we have epsilon tensor 1C delta C is equal to n eta C. I will indicate what is n eta C, and equal n eta C. Let's say n eta C bar. Then we say that the coalgebra has a co-unit, and that co-unit is given by this. Okay. N eta C is just the isomorphism from C to K times C, and the other one is the isomorphism from C to C times K. Okay. Now that the structure of coalgebra has been defined clearly, we can look, we can check the co-derivation of the differential of the, on the coalgebra. So CD is the coalgebra if the differential here is the co-derivation for the co-multiplication defined here. Means that we have here C times C Here we have a co-multiplication. We have here DC tensor the identity plus 1 tensor 1C the identity. Tensor this, and we have here C tensor C. Have here D. Have here C. Voilà. So we have this diagram is commutative. This is equivalent to say that DC tensor the identity map plus the identity map tensor DC is equal to composite by delta. The co-multiplication is equal to D to delta C composite by DC. Voilà. Okay. So if D satisfies this property, we say that D is a co-derivation for this co-multiplication. The notion of coalgebra, algebra, differential guided module, and so on has already been defined. So we are going to apply. You know that the algebraic topology is a way to combine the algebra structure and the topology. So here we are trying we are going to try to transfer all this property to the topological, to some topological space. So we are moving to the notion of singular homology. Okay. Is there any questions? Okay, let us go on. Okay, singular homology. Singular homology. So here we consider X a topological space, object of the category of topology. We consider here delta, we call it n standard simplex, which is equal to, yes. Okay. 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 It's okay. It's okay. Okay. Which is equal to from 0 for this summation delta n, which is the n simplex standard, which is defined by Ti Ei, which Ti from 0 to 1 and summation of T I from 0 to n is equal to 1. So this set is a subset of R n plus 1, and Ei here, I from 0 to n is the standard basis, the canonical basis of R n plus 1. Okay. Now we consider here a topological space. We consider the n standard simplex here. This is a topological space endowed with the topology coming from this topological space. So, we will define firstly the notion of n singular simplex. Definition, let me put it here. Okay. If we consider X a topological space as said before, we call n singular simplex a continuous map delta n defined from delta n to X. So a continuous map from the n standard simplex to the topological space is the singular simplex on X. And the set of all n singular simplex is denoted by this. Moreover, if X and Y are two topological space and phi is a continuous map, we can define this map can be transferred to the n singular simplex like this, which assigned to any here we have Sn phi applied to sigma n, which is equal to, we just have to decompose it. Let me draw it. We have here delta n to X, and here we have phi, that's the continuous map given up there. We have this composite here. So this is equal to composite by sigma n. Oh, okay. Okay, it's okay. It's okay. So, faut que j'écrive là-bas. So, we have a link between two topological space. With this link, which is a phi here, we have the link between the related n simplex here by this map. Okay. Let us give some examples of simplex. If we consider X a particular topological space, which is a convex world, we call it in French envelope convexe of Rn plus 1. We consider x1, x0, x1, xn element of X. We can define a map X denoted by x0, x1, x2 up to xn from delta n to X, which assigned to any element here, Ti, Ei, the summation from 0 to n, Ti, Xi. Don't forget that our delta n is equal to the summation from 0 to n, Ti, with Ti from 0 to n, and the summation of Ti is equal to 1. Keep it in mind. So we have this map. This map is a continuous map. The topology here is the one induced from the topology in Rn plus 1. Here we also have the topology induced by the one on this topological space. So this map is obviously a continuous map. This is an example of n simplex. Another useful n simplex is lambda I. Is lambda I defined from delta n -1 to delta n, which assigned to any element here, Ti, Ei, lambda I. Let us denote it by this, of summation from 1, G here from 0 to n -1, Tg, Eg, equal to what? Equal to summation of G from 0 to n, T prime G, T prime J, A, G. So that we have this condition here. Means that T prime G here is T prime J here is equal to T J. If you have this condition, is equal to 0. If you have this condition, is equal to T G -1. If you have this condition. The second useful map is this one, rho G, rho I, defined from delta n to delta n, which assigned to from 0 to n plus 1, T G, summation from 0 to n, T prime which the condition below here, have this condition here. Okay. So with these two useful maps, we can define let us say something about these two maps. This one is called the phase, the I phase. It's called the I phase, and this one is called the I degeneracy. Voilà. So by using these two maps, we are going to define some linear maps as follow. Delta I defined from okay. Defined from Sn of x to Sn of x, which assigned to one here. We map from delta n to x, delta I of sigma n equal to, okay, we have this. We have defined the map lambda here, and the one here. So we have here delta n plus 1 to x. And before that, we have here delta n to this. So we have here lambda I here. So this composite is just sigma n plus 1 composite by lambda I. Okay. And this is the I phase linear map. In a similar way, we define the degeneracy maps defined from S n of x to S n plus 1 of x, which assign to, let me define it in the other, on the other side. So we have here sigma n, and using the map using this map, which is defined from delta n we have here okay, sigma is defined from CISO. Okay, have this. Okay, so with these two map, we'll get we'll go directly to the construction of the singular chain complex. So to define the singular chain complex, we start with the definition of a graduate module denoted by this. This is some problem about it. Voilà, on passe plus. Okay. So to define the singular chain complex, we start with the definition of something denoted by this, which is a graduate module. This is indeed the graduate module, the free graduate module. Let me say it that like this: free graduate module generated by that is, for all n belonging to n Cn of x k is just the module generated by this. Equivalent to say that all sigma, let's say A in Cn of x k, A is equal to summation sigma belonging to Sn alpha sigma dot sigma dot sigma. This summation is a finite summation, means that all the coefficients here which are in k are 0 except a finite number, and sigma belong to sigma n here is a n-Sembler simplex. From the E, from the I, from delta I here and Si, we are going to define a linear map on this graduate module. D is defined from C star x k to C star x k, such that for all I belonging to n, di of Ci of x k to Ci negative 1 x k is just defined like this. I will define it on the generator here, and we can extend it to the whole graduate module by linearity. So di of sigma is equal to summation I from let's say g from 1 from 0 to I negative 1 power I delta I, here is g of sigma, and here sigma here sigma I, okay, of this formula. So di here is defined on the generator of this free graduate module by this formula. We can extend it to the whole module by linearity. Now we have defined this graduate module. We have defined on this graduate module the differential. It is by calculation that it is shown by calculation that this is equal to 0. Means that this is a differential, as we see before. So is called the singular chain complex. Okay. We have defined the singular chain complex. We can define the dual notion of this notion, which is the cochain complex. We saw that if A and B are two complexes, or if A is a complex, a chain complex, then ohm of A k is which is a dual of A is a cochain complex. We'll apply it here. We consider R to be equal to this chain complex, and then we have a new graduate module denoted by this and equal to ohm k of which is the cochain complex of x with coefficient in k. And the differential is the one I defined before. So having the chain complex and the cochain complex, we have defined the notion of homology and cohomology, respectively associated to the chain complex and the cochain complex. This notion of homology can also be transferred here to the chain complex, and the cohomology to the notion of cochain complex, and we have the notion of singular homology of X. We have the notion of singular homology of X, denoted generally by this, which is indeed equal to this is for the homology, and for the cohomology we have the notion of homology, of course, has been defined before, related to the notion of chain and cochain. So the related notion associated to the notion of singular simplest cochain and singular simplest chain are the following one. Now, we are trying to build the link between topology and algebra. Now that we have the information about the cochain and chain complex related to X, we are going to study the link between the maps in the topology category to the category of chain complex. So if X is a topological space, Y topological space, F a continuous map, so this is the map in this category. We have, okay. Voilà. So if F is a map in this category, we have the following map in the category of chain complex, singular chain complex. We can move also from this category to the category of cochain complex. So this functor is a covariant functor, and this one is a variant functor, and this one is covariant functor. Because we have reversed we have changed the position of X and Y here. And obviously we'll also have so we can also move from the category of topological space to the category of graduate module with the functor, with the homology functor, and with the cohomology functor. This notion is can be well defined. So normally, if we consider here, we have here C star of F applied to sigma n is equal to F. We have F composite by sigma n, something like this. So we can also define this one in a similar way. Okay. Now we have defined the notion of singular quotient, singular cohomology, singular cohomology, and so on. So we are going to, at the beginning I have used the notion of normalized singular quotient. How I use it. We are moving to this term, to this notion. Okay, we are going to define it. Okay, there's a problem. Okay. Okay, we are going to define it. So to define it, let us define first the set of all n simplex of this form. Si has been defined before. The set of all these n plus 1 n simplex, because this is n plus 1. Okay. The set of these generate a submodule of C x of this chain complex, and the set of this set is denoted by D. What I'm trying to say here is that if we consider the set of all simplexes, n simplexes of this form, then this set generate a submodule of this, and so this submodule can be, we have this is a submodule of this. We can take the quotient of the module by the submodule and obtain what we call the quotient module. When you have the quotient module, GCXK is a submodule of CXK. By taking the quotient, we have a new complex which is called the normalized singular quotient, normalized singular chain of X, normalized singular chain of X with coefficient in K. Okay, it is proved that this is a subcomplex of this one. So the differential here is the one coming from the complex here. It's just the restriction of the differential here to that subcomplex. So we can compute here the homology of this one. And since the element, the generator here are the degeneracy, so the homology of this is 0. And we have what? We have this short exact sequence. We have D, C, X, K, D, C, X, K, go to C, X, K, go to N, X, K to 0. Have this short exact sequence. let me write it here again, so that should be very clear for all of us. Here we have, this is a short exact sequence. Okay, so by taking the homology, we have this. Have this isomorphism as a graduate vector space. This is why when you are working in homology, you have to precise if you are working with the normalized or the unnormalized singular quotient, because in homology the two are the same. Okay. Is there any questions? If there is a question, so maybe it is time that I should answer to a few questions before we go to the end of the first part of this course. No question? Okay, if there's no questions, the first part, let me give the summarize of what we did this evening, so sorry. This evening we start with the graduate module, differential graduate module. We define the complex and the complex, the chain complex and the quotient complex. We define the graduate algebra, the differential graduate algebra, and then we move to the singular homology. We define what we call singular chain complex of a given topological space X, what we call the normalized singular chain complex, and we said we obtain the results, the following results, which say that the homology of the normalized and the unnormalized singular chain complex is the homology are equal. This is what we did this evening. So tomorrow we'll go on with the notion of projective resolution, semi-free resolution. So tomorrow we'll go directly to the subject of these lectures. So with this notion of semi-free, we'll be able to define the notion of Allen-Benmore differential tau, and then show the link between the Hochschild homology and the Allen-Benmore differential tau, the link between the normalized, the free loop space homology and the Allen-Benmore differential tau, and then at the end we'll show the link between the algebra link between the two differential tau. Thank you for your kind attention.